In this session, we are going to continue our exploration of subtyping in generics. In particular, we're going to discuss the important and somewhat tricky concept of variance, which means how subtyping relates to genericity. The material in this session might be a little harder than what you've seen previously. If you want to go fast and you don't need to know things to the last detail, then it's perfectly fine if you just browse this session or skip it completely. On the other hand, if you want to go to the roots, then the session is for you. As a bonus, we're going to develop a completely satisfactory model of cons lists that doesn't have any of the shortcomings that we had to deal with before. You've seen in the previous session that some types, such as list, should be covariant, whereas other types, such as arrays, should be not covariant. What's the difference between the two? Well, roughly speaking, the type list is immutable, whereas the type array is mutable because we can update its elements. And immutable types can typically be covariant if some additional conditions or methods are met, whereas mutable types cannot. In this session, we will find out precisely what the conditions are, so when types can be covariant and when they cannot. In fact, it's not just a binary choice between variant or not. There are actually three possible relationships between type instance C of C and A and C and B, where C of T is a parameterized type, and A and B are types such that A is a subtype of B. So we could either determine that C of A is a subtype of C of B. Or we could determine the opposite relationship, which would say that C of B is a subtype of C of A. Or we could have the relationship where neither of the three was true. So neither C of A is a subtype of C of B, nor is C of B a subtype of the other. So if C of A is a subtype of C of B, we say C is covariant. If the opposite is true, so C of A is a supertype of C of B, then we say C is contravariant. And if neither of the two are true, then we say C is non-variant. Scala lets you declare the variance of a type by annotating the type parameter. So you can determine that a class should be covariant by writing a plus in front of the type parameter, the A here. Or you could determine that it's contravariant by writing a minus. Or finally, if you write neither plus or minus, then the default is that C is non-variant. So C of A and C of B are unrelated. So here's some food for thought. Say you have two function types. The type A is a function that takes int set to non-empty set, and type B is a type that takes non-empty sets to general int sets. According to the Liskov substitution principle that you've seen in the last session, which of the following should be true? Is A a subtype of B, or B a subtype of A, or are A and B unrelated? So I will argue that type A is a subtype of type B. Why? Well, let's look. What can you do with a type B, a function from non-empty to int set? Well, the thing you can do is you can pass a non-empty set to it and receive an int set back. Can you do the same thing with type A? Well, of course, if you pass a non-empty int set to the type A, it expects just an int set, so non-empty int set will do just fine. And you will get back a non-empty set, which of course is a special case for an int set. So type A satisfies the same contract as type B. If you give it a non-empty set, it will give you back an int set, but it actually will satisfy more than B. So that's why A is a true subtype of B. So let's generalize this to arbitrary function types. So the rule we have is if we have two function types a1 to b1 and A2 to B2, then the first is a subtype of the second if first the result types B1 and B2 are subtypes, so they go in the same direction, but the argument types go in the other direction. So A2 must be a subtype of A1. So let's express that visually. So we have the supertype A2 to B2 here, and the presumed subtype A1 to B1. So what we say is that the A2 type is a subtype of A1 and B1 is a subtype of B2. And that would mean that this is a special case of the A2 to B2 function. Why would that be? Let's see. Let's look at the first function. So all we could do is pass an argument of type A2 into this function. Because of this subtyping relationship, we can pass the same argument also to A1, because A2 is a subtype of A1. Then we apply the function A1 to B1. That gives us a B1. And again, because of subtyping, that actually qualifies as a B2. So we could easily, instead of having used this function here, we could supply the lower function over there, and the same argument types would map to the same result types. So what we've learned is that functions are actually contravariant in their argument types and covariant in their result types. We can then express that in code in Scala, and that leads us to the revised definition of the function one trait that you've seen before. So now I've added two variance annotations to the parameters. The argument type t is contravariant, it has a minus, and the result type u is covariant, it has a plus. Now, can we just sprinkle minuses and pluses over classes as we please to make them co or contravariant? Well, obviously not, because otherwise we could have done the same thing with array, make array, for instance, covariant, and run into the same soundness problem that Java did. So there are rules when can we annotate a type parameter with plus and with minus. So to find out what the rules are, let's look again at the array example. So I now assume that array is a class, written like this one, array, and update, the updating functionality in array is captured as a method, call it update. So the problematic combination was that the class was covariant, so the type parameter t had a plus here, whereas update took a parameter of the same type t. So a covariant type parameter t together with a method that takes a parameter of that type will lead to problems, or did lead to problems in the array case. So the Scala compiler will actually check that there are no problematic combinations when compiling a class with variant annotations. Roughly what it will do is it will let covariant type parameters only appear in method results. Contravariant type parameters can only appear in method parameters, and non-variant or invariant, that they are used as aliases, type parameters can actually appear anywhere. The precise rules are a bit more involved, but fortunately the Scala compiler will perform them for us, so we don't need to memorize them all. If we go back to the function example, the checks that the Scala compiler will perform here is that the t parameter, which is contravariant, is only used as a function parameter. That's correct. And the u parameter, which is covariant, is only used as a function result, which is also correct. So function 1 checks out okay according to these checks. So now that we've seen variance, let's get back to the previous implementation that we did of lists. One shortcoming there that was that nil was modeled as a class, whereas we would prefer it to be an object. After all, there's only one empty list. Can we change that? Well, let's have a look at the example. So I've brought up the list hierarchy that we've seen in previous sessions. What we would like to do is turn class nil into an object. So let's just go right ahead and do that. So objects can't have type parameters because there's only a single instance of them. So I will delete the type parameter for the object. Then we get an error which says that the type t here is not found. That's true because t is no longer bound as a type parameter. So we have to find another type in which we want to use as the argument type of type list. What would be a good type? Well, of course, we could write list of string or list of object, but all of that would make nil only a subtype of a specific kind of list. So what we will try instead is make it a list of nothing. That's promising because, as we know, nothing is the bottom type, which is a subtype of every other type. So it's in a sense universal. It can express everything else. But we're not done yet. To see why, let's make a little test object and say here I want to have a simple assignment where I say valx of type list of string, and that should be the empty list. We get an error which says, it's a long error message, which says, well, it found a nil and it required a list of string. So obviously nil is not a subtype of list of string. And then it goes on to say, you may wish to define the type parameter t of list as plus t instead. So what the compiler suggests is that indeed we should make lists covariant. And that we make by having a type parameter here. If we do that, then everything will type check correctly. So let's have a look at what happened here. So list of string equals nil type checks because nil is a list of nothing. Nothing is a subtype of string, and lists are covariants. So that's why list of nothing is a subtype of list of string. Another thing that works out very well here is that we have seen that in the object nil, head and tail already return nothing because they can't terminate. And that matches precisely the template of list, because we said for a list of t, head should return a t and tail should return a list of t. Now, head indeed does return the element type here, nothing. Tail doesn't return a list of nothing, but directly a nothing. But that's actually something that's even a subtype of list of nothing. So both types are very, very precise in what they express. To complete this session, which was quite a bit harder than previous sessions, I want to introduce one more thing. Sometimes we actually have to put in a bit of work to make a class covariant. So to see an example is, let's say we want to add a method prepend to our list class, which prepends a given element and yields a new list. So prepend would be defined like this. It would say, take an element of type t, the element type of the list, give me back a list of t. And it would have the obvious implementation. It would create a new const cell with the given element, followed by the current list itself. But that doesn't work. Why does it not work? So I leave this for you as an exercise. Why does the following code not type check? The prepend method as before in a covariant list. Possible answers are: prepend turns list into a mutable class, prepend fails variance checking, or prepend's right-hand side contains a type error. What do you think? Well, one way to solve this is try it out. Put prepend in, let's put prepend into our worksheet and see what happens. So what we get is an error which says covariant type t occurs in contravariant position in type t of value lm. What that says is that our covariant type parameter t appeared as the type of a method parameter, and we've seen that that actually violates the variance checking rule. So the variance checking rule, which was actually invented to prevent mutable operations in covariant classes, also rules out something like this, which doesn't involve any mutability at all. All we do is create a new list. Do you think that's a mistake of the rules, or is there some deep wisdom to the rules nevertheless? In fact, the Scala compiler is right to throw out list with prepend Because it does violate the Liskov substitution principle. Why? Well, here's something one can do with a list of type list of inset, called the list XS. We can do xs.prepend empty, because empty, of course, is an inset. But the same operation on a list ys of type list of non-empty would lead to a type error. So if we did that, ys.prepend empty, then you would see a type error message like this one here, which says, well, we required a non-empty because that was the element type of the list, but we found an empty, and the two are not compatible. So here's something you can do with a list of inset that you cannot do with a list of non-empty set. And because we found such a thing, it follows that according to the Liskov substitution principle, list of non-empty cannot be a subtype of list of inset. Okay, so now we know why prepend is illegal, but still there's an unsatisfactory feeling here, because prepend is a natural method after all to have on immutable lists. So the question is, can we somehow make it variance correct? And in fact we can, and for that we will make use of a lower bound. So here's a reformulation of prepend which uses a lower bound for the type parameter u. We say prepend, it takes a type parameter u, which must be a supertype of the list element type t. It takes a new element now of type u, and it returns a list of u. And the body of prepend is as it was before. And actually, this passes the variance checks, because it turns out that covariant type parameters, such as a t of list, may appear in the lower bounds of method type parameters. Contravariant type parameters may appear in the upper bounds instead. So you can find out yourself how this works in detail by solving the following exercise. Implement prepend as shown in trait list. The question is, let's say we have a function that takes a list of non-empty as first parameter and an empty element as second parameter, and it prepends the empty list set to the list of non-empty sets. What would happen? The possible answers are this would not type check, or the result type of this function would be a list of non-empty, or maybe a list of empty, or a list of int set, or a list of any, the top type of all Scala types. What do you think? Now let's see how we would solve that. The straightforward way to attack this is, well, let's try it out. Let's add the function prepend and the function f as we've seen on the slide. And if we look at the function f, its type when we hover over f would say it takes a list of non-empty and an empty, the parameters as given, and it returns a list of inset. So list of inset is the correct answer. That still begs the explanation why. So let's look first at the subtype hierarchy. As always, we have that inset is a supertype of both non-empty and empty. So we call the predef method on a list of non-empty. So t in this case for the predef method, that is non-empty. That was the parameter of the list. But t takes a type parameter which can be an arbitrary supertype of non-empty. And one thing that must happen with this supertype is that lm is an instance of the supertype. So lm, the type u, that is empty, because that's the type of the x that we pass to predef. Is empty a subtype of non-empty? No, of course not. So that's why the empty value that we pass in here, it doesn't conform to the non-empty type. So what the type inferencer would choose instead is the next higher type up here, so that would be intset. Maybe U can be an intset, and indeed that would work out. The list XS, which is a list of non-empty, is of course also a list of intset because of covariance of lists. And empty is itself an intset. So the type inferencer would determine that the correct type parameter for U indeed must be intset, and the type that gets returned from prepend is then a list of intset, and that's then also the result type of F. So one thing we've seen here is that intuitively F does exactly the right thing. If we take a list of non-empties and we add an empty, the best thing that we could get out of that would be a list of insets, because that's the smallest type, in a manner of speaking, that contains both the XS, the list of non-empties, as well as the additional element X, which was of type empty. So we see that the machinery with the subtype bound here, it is a little bit complicated, but on the other hand, it does exactly the right thing. It will lead to exactly the right inferred types for data structures that contain elements of various different types.